When I ask what it would mean for the cosmos to be a prison, I have to translate that idea into physics. A prison is a place you cannot escape from. It has walls, limits, and rules that constrain motion. So the scientific version of the question becomes, are there fundamental limits on where anything in the universe can go, what it can do, and what it can know? And if so, what in modern cosmology creates those limits? The first thing I need to do is strip away the human meaning of the word prison. The universe is not designed. It is not trying to trap us. But it does have structure. It has laws. Those laws define what is possible. When I talk about the cosmos as a prison, I'm really asking how gravity, dark matter, dark energy, and space-time itself restrict motion and information, and how those restrictions shape the fate of everything. To understand this, I start with gravity and space-time. In modern physics, gravity is not a force pulling on objects in the old Newtonian sense. In general relativity, gravity is the curvature of space-time caused by energy and mass. Matter tells space-time how to curve. Curved space-time tells matter how to move. When I draw that in my mind, I imagine a flexible fabric. If I put a heavy ball on that fabric, it sags. Smaller balls roll around in curved paths. They are trapped in orbits, not by invisible strings, but by the geometry itself. This idea scales up. Galaxies orbit within clusters. Stars orbit within galaxies. Planets orbit stars. In each case, gravity defines regions where objects are bound together. A bound system is one where the total energy is not enough to escape. If you launch a rocket from Earth slower than escape velocity, it falls back. The Earth's gravity well is a simple example of a local gravitational prison. You can escape it, but only by paying an energy cost that exceeds a threshold. On cosmic scales, gravity builds even deeper wells. The most extreme are black holes. A black hole is a region where space-time is curved so strongly that beyond a certain boundary called the event horizon, all future paths lead inward. Not even light can climb back out. That is a clear, physical, no-escape region. The boundary is not made of matter. It is a surface in space-time where the structure of light cones tilts so far inward that all possible motion is trapped. We know black holes exist from multiple lines of evidence. We see stars orbiting invisible massive objects, like at the center of our galaxy, where stars whip around something with about 4 million times the mass of the Sun in a very small volume. We detect gravitational waves from black hole mergers, ripples in spacetime that match the predictions of general relativity with high precision. We have even imaged the shadow of a black hole, the dark silhouette against glowing gas, using the Event Horizon Telescope. All of this tells me that nature creates true gravitational prisons, where information that falls in cannot return to the outside universe in any classical sense. But black holes are local structures. The question, is the cosmos a prison, is bigger. It asks about the entire universe as a whole. For that, I have to talk about cosmic expansion, dark matter, and dark energy. On large scales, the universe is expanding. Galaxies are, on average, moving away from each other. This is not because they are flying through space like shrapnel from an explosion. Instead, the space between them is stretching. We discovered this in the 1920s when Edwin Hubble and others measured redshifts of galaxies. The light from distant galaxies is shifted to longer wavelengths. The farther away a galaxy is, the larger the redshift. This relation, now called Hubble's law, is strong evidence for an expanding universe. We interpret these redshifts using general relativity. The simplest large-scale solution is a universe that is homogeneous and isotropic on average, meaning it looks similar in all directions and at all locations when you smooth over small-scale structure. In that framework, the expansion is described by a scale factor, a function of time that tells me how distances between unbound objects change. The rate of change of that scale factor is the Hubble parameter. When we look at galaxies billions of light years away, we are looking back in time. By measuring redshifts and distances for many galaxies and supernovae, we can reconstruct how the expansion rate has changed over cosmic history. In the late 1990s, two independent teams studying distant Type Ia supernovae found that the expansion of the universe is accelerating. The light from those supernovae was dimmer than expected if the expansion were slowing under the pull of gravity from matter. The simplest way to explain this is to add a component to the universe that has negative pressure. In general relativity, pressure also gravitates. A component with sufficiently negative pressure causes a repulsive effect on large scales, driving accelerated expansion. We call this dark energy. We do not know what dark energy is at a fundamental level. The simplest model is a cosmological constant, a constant energy density of the vacuum itself. This fits current data quite well. The cosmic microwave background, the afterglow of the hot Big Bang, shows tiny fluctuations in temperature and polarization. The pattern of these fluctuations, combined with galaxy clustering and supernova data, tells us that about 68 to 70% of the energy content of the universe today is in this dark energy component. About 25 to 27% is dark matter. Only about 5% is ordinary matter: atoms, stars, gas, planets, and us. Dark matter is another kind of cosmic constraint. We infer its existence from gravity. Galaxies rotate too fast in their outer regions if we only count visible matter. Clusters of galaxies need more mass to stay bound than we see in stars and gas. Gravitational lensing, the bending of light by mass, shows that there is more mass present than luminous matter accounts for. The cosmic microwave background also encodes the total amount of matter and how it clumps. All of these lines of evidence point to dark matter, some kind of non-luminous, non-baryonic matter that interacts gravitationally and perhaps weakly, but not with light. Dark matter forms a kind of invisible scaffolding. It collapses under its own gravity into halos. Ordinary gas falls into these halos, cools, and forms stars and galaxies. The large-scale structure of the universe, the cosmic web of filaments and voids, is shaped by dark matter. In that sense, dark matter defines where structure can exist and how it evolves. It is not a prison in the emotional sense, but it is a framework that constrains the motion of galaxies and the growth of cosmic structure. Now, dark energy changes the story of cosmic constraint in a different way. In a universe with only matter and radiation, the expansion would slow over time. Gravity would pull everything together. Whether the universe would eventually recollapse in a big crunch or expand forever at a decelerating rate would depend on the total density. In a matter-only universe that recollapses, you could say the cosmos forms a kind of global gravitational prison. All matter would eventually fall back together. Our universe does not seem to be heading for a big crunch. With dark energy dominating, the expansion is speeding up. Over time, this acceleration has a dramatic consequence. Distant galaxies that are not gravitationally bound to us will recede faster and faster. There is a subtle but important point here. The speed limit set by the speed of light applies to motion through space. The expansion of space itself is not limited in the same way. As the universe expands, there is a distance beyond which galaxies recede from us faster than light due to the stretching of spacetime. Light emitted now from beyond a certain horizon will never reach us in the future. This defines a cosmic event horizon, similar in concept to a black hole horizon, but on a cosmological scale. There is a finite region of the universe that can ever send signals to us and that we can ever influence. As dark energy continues to dominate, this region shrinks in comoving coordinates. More and more galaxies cross beyond our event horizon. They do not disappear locally, but their light can no longer reach us after some time. From our point of view, the observable universe becomes more and more empty. In this sense, accelerated expansion creates a different kind of prison. It does not trap everything together. It isolates everything from everything else. Gravitationally bound structures, like our local group of galaxies, will stay together. The Milky Way and Andromeda will likely merge in several billion years, forming an elliptical galaxy. The local group will remain bound despite cosmic expansion, because gravity inside that structure is stronger than the effect of dark energy on that scale. But beyond that bound region, galaxies will drift away beyond our horizon. We know this from solving the equations of general relativity with a cosmological constant and matter. We plug in the measured values of the Hubble constant, the matter density, and the dark energy density. We then evolve the scale factor forward in time. The solution shows a universe that approaches a de Sitter state, exponential expansion driven by a constant dark energy density. In that state, an event horizon exists with a fixed physical radius set by the value of the cosmological constant. Anything beyond that radius is forever causally disconnected from us. So is that a prison? From a physics standpoint, it is a hard limit on what regions of the universe can exchange information. No signal, no matter how advanced the technology, can cross a cosmic event horizon from one side to the other in finite time. That is a structural feature of spacetime itself in an accelerating universe. It is not negotiable. It is not a matter of engineering. It is built into the geometry. At the same time, within the region that remains causally connected, there are other constraints. The speed of light is an absolute limit for information transfer in special and general relativity. No object with mass can be accelerated to or beyond the speed of light. This is not just a technological challenge. It is a consequence of the way energy, momentum, and spacetime are related. As a massive particle approaches the speed of light, its energy grows without bound. You would need infinite energy to reach light speed. So there is no way to outrun the expansion by going faster than light. That phrase does not even make sense in the framework of relativity. The combination of these facts means that, even in principle, there are regions of the universe we can never reach or observe. There are also regions that could never reach us, even if there were civilizations there trying to do so. The universe is partitioned into causally separate domains by its expansion history and energy content. When I think of the cosmos as a prison in this technical sense, I see a network of horizons. Black hole horizons around collapsed objects, cosmological horizons set by dark energy, particle horizons set by the finite age of the universe and the finite speed of light. Each horizon is a boundary of knowledge and influence. We also face observational limits that are not about future horizons, but about the past. The universe was once hot and dense. As it expanded, it cooled. About 380,000 years after the Big Bang, the temperature dropped enough for electrons and protons to combine into neutral hydrogen. Before that, the universe was a plasma, opaque to light. After recombination, photons could travel freely. The cosmic microwave background is the relic radiation from that time, now stretched to microwave wavelengths by the expansion. When we observe the cosmic microwave background, we are looking as far back in time as light can show us. We cannot see earlier with electromagnetic radiation because the universe was opaque. In principle, we can probe earlier times with neutrinos or gravitational waves, which decouple earlier. A cosmic neutrino background and a primordial gravitational wave background should exist. We have strong indirect evidence for the neutrino background, but not a direct detection yet. We have upper limits on primordial gravitational waves from the polarization of the cosmic microwave background, but no confirmed detection. Even if we detect them, there will still be a limit. We cannot access the initial condition of the universe before some earliest time. Quantum gravity effects, which we do not yet fully understand, will likely set a fundamental boundary on what can be known about the beginning. So the cosmos, as we understand it, has multiple layers of inaccessibility. Regions we cannot reach because of expansion. Times we cannot see because of opacity and quantum limits. energies we cannot achieve because of practical and fundamental constraints. The laws of physics themselves define these boundaries. Now I want to be clear about what we know and what we do not know in this picture. We have strong evidence for cosmic expansion from galaxy redshifts, the cosmic microwave background, and large-scale structure. We have strong evidence for dark matter from galaxy rotation curves, gravitational lensing, cluster dynamics, and cosmological fits. We have strong evidence for dark energy and accelerated expansion from supernovae, the cosmic microwave background, and baryon acoustic oscillations. We have a theory, general relativity, that has passed every experimental test so far in the regimes where we can test it. But there are open questions. We do not know the exact nature of dark matter. It could be one or more new particles, like weakly interacting massive particles, axions, or something more complex. Direct detection experiments have not yet found a signal. We are narrowing down the possibilities, but the identity of dark matter remains unknown. That uncertainty affects the details of how structure forms, but not the basic fact that dark matter is there in some form. We also do not know what dark energy is. The cosmological constant model works well, a constant energy density of the vacuum, with an equation of state parameter W-1, meaning its pressure is negative and equal in magnitude to its energy density. Observations so far are consistent with W being -1 within a few percent. But we cannot rule out that dark energy might evolve slowly with time, or that our theory of gravity might need modification on the largest scales. If dark energy is truly constant, the universe will asymptotically approach a de Sitter state. If dark energy changes, the future could be different. In extreme models, dark energy could grow stronger over time, leading to a big rip where even bound structures are eventually torn apart. Current data do not favor such extreme scenarios, but the door is not completely closed. We also do not have a complete theory of quantum gravity. General relativity is a classical theory. Quantum field theory describes matter and non-gravitational forces. Combining them consistently at very high energies or very small scales is an open problem. Without a quantum theory of gravity, our understanding of the very early universe and of what happens at the singularities inside black holes is incomplete. The singularities in classical general relativity are signals that the theory breaks down. They may be replaced by something finite and well-defined in a quantum theory, but we do not know yet. These gaps in knowledge matter for the prison question. For example, information that falls into a black hole seems lost from the perspective of an outside observer, but quantum mechanics says information should not be destroyed. This is the black hole information paradox. Many physicists think that in a full quantum gravity theory, information is not truly lost, and that black hole evaporation through Hawking radiation encodes the information in subtle correlations. If that is correct, then black holes are not perfect prisons for information, though they are still practical prisons for any physical object that falls in. On cosmological scales, we might also ask whether the cosmic event horizon truly hides information forever, or whether quantum effects change the story. There are ideas about horizon entropy, de Sitter thermodynamics, and holography that suggest deep connections between horizons, information, and the fundamental description of spacetime. These ideas are active research areas. They are not settled. I have to be honest that at this frontier, our language becomes more speculative. We have mathematical frameworks and hints, but not a complete, experimentally tested theory. From a practical standpoint, though, the constraints imposed by dark energy and cosmic expansion are robust. If dark energy is close to a cosmological constant, then in the far future, distant galaxies will be redshifted so much that their light becomes undetectable. The cosmic microwave background itself will be stretched to wavelengths larger than the observable universe. Future observers, living trillions of years from now in a bound galaxy group, would see only their local structure. They would have no direct observational evidence of the Big Bang or of cosmic expansion. For them, the universe would look static and isolated. The large-scale cosmos would be effectively hidden behind a horizon of redshift and darkness. In that future, the physical prison is not a wall, but a loss of access to evidence. The information about the wider universe would still exist in principle, but no new signals would arrive from beyond the local group. The cosmic laboratory would shrink. The range of experiments and observations possible would narrow. That is a different kind of confinement. A limit on knowledge imposed by the dynamics of space-time and the finite speed of light. Even today, our observable universe is finite. The particle horizon, the maximum distance from which light could have traveled to us since the Big Bang, is about 46 billion light-years. Beyond that, there may be more universe, perhaps infinitely more, but we cannot see it. We infer its properties by assuming that the universe is statistically similar beyond our horizon. That assumption, called the cosmological principle, is supported by what we see within our horizon, but it is still an assumption. We cannot test it directly beyond the boundary of what light has had time to reach us from. So, in multiple ways, the cosmos sets boundaries. It sets a maximum speed for information. It sets horizons in space and time. It locks some regions behind black hole event horizons. It hides the earliest moments behind quantum and opacity limits. It may hide parts of itself forever beyond a cosmic event horizon driven by dark energy. These are not human-made prisons. They are the structure of reality as far as we can tell. At the same time, the laws that impose these limits also make the universe intelligible. The same general relativity that gives us black holes and horizons also explains the orbits of planets and the expansion of space. The same dark matter that hides from our detectors shapes the galaxies we see. The same dark energy that will isolate our local group in the far future made it possible for structures to form in the first place by not dominating too early. The constraints and the possibilities come from the same underlying physics. When I ask whether the cosmos is a prison, in the strict physical sense, my answer is that the universe has built-in limits on motion, communication, and knowledge that no technology can overcome. Those limits come from gravity, space-time geometry, and the energy content of the universe, especially dark matter and dark energy. Within those limits, there is enormous room for complexity, structure, and exploration. Beyond those limits, there is simply no access. The deepest open question for me is this: are these horizons and limits truly fundamental, or are they emergent features of a deeper theory we do not yet have? In other words, if we someday understand quantum gravity and the true nature of dark energy and dark matter, will the cosmic event horizon and black hole horizons still be absolute boundaries? Or will they turn out to be approximate descriptions hiding a more subtle, possibly more connected, underlying reality? We do not know yet, and answering that is one of the central challenges of modern theoretical physics.